All right, so it's me again, and we just finished up doing like the intro with all those terms. We got into energy. So now what we're doing is we're going into the laws, the laws that are out there on energy. Let me kind of try and cover some of this up so we're just focusing on this. All right. And when we start talking about these laws, first we got to get a few terms down. Okay. And the first one is thermodynamics. It sounds so impressive when you say, oh, I'm studying thermodynamics. It sounds so impressive. But really, what is it? It's the study of the energy transformations that occur in a collection of matter. Let's say that again and I'll write it out. It's the study of energy transformations. So it's the changing of energy forms, transformations. Am I going to put this all in here? Yes, I am. Okay, transformations that occur in a collection of matter. So in other words, what is this collection of matter? Well, it's whatever you're studying. So if you're studying a worm, then it's the worm is the collection of matter. And you're going to talk about the energy transformations that go on inside that worm. If you're studying a person, it's that person. If you're studying your dog, it's that dog. If you're studying a population, it's all the energy transformations that are going on inside that population. Okay, so that collection of matter can be as big or small as like what you're studying at that moment. Okay, now, so what is this collection of matter? Well, we actually give it a term. We call it the system. Okay, so the system is what is being studied. Okay, it's the matter under study. The matter under study. So it's like that worm that you're talking about or something. And there's two types of systems: isolated, which are unable to be affected by the surroundings, okay, and open, that are affected by the surroundings. So isolated, unable to exchange, let's say, exchange with surroundings. Oh, I forgot the I-N-G-S, surroundings. Surroundings, yes. Okay, sorry, my spelling sometimes. And open is definitely may transfer energy between the systems. So may exchange, we'll keep them similar, exchange with surroundings. So you might say, well, isn't everything going to be affected by the surroundings? To a certain extent. And it brings me to a story. Okay, I know you like my stories. So it's kind of a funny story. I had this thermos, and I had to take my mom into the hospital the one day for some tests. And it turns out I was having a test the next day. And I couldn't eat anything but clear broth, right? So I knew I was going to be there for a while with her. So I decided to take some clear broth soup, like in a thermos. And so I got this thermos and I thought, oh, this is great. This thermos will keep the soup warm because I don't like cold soup. I don't know about you guys, but I don't like cold soup. My thermos was an isolated system and I wasn't thinking. Okay. So I heated up that soup that morning, put the boiling soup broth into the thermos, sealed the thermos up, and it became an isolated thing. It was not exchanging with the surroundings because if you have enough insulation around something, then what's going on inside is not going to be affected by the outside. Okay, so that was an isolated situation. So then it comes time to eat, and of course I'm sitting in this doctor's office and it says no food, and I'm like, well, there's drinks though, are okay. So I go to drink out of this thermos. So I open up the thermos. Remember, it's been isolated this whole time. Put in that boiling soup, right? Go to open it up. I go to drink the soup out of it, and it had this really weird spout where I thought the soup was going to come out. I put my mouth on that part, ready to take a sip of this soup. Instead, it kind of came out the side, Well, there I was, and this hot soup is pouring down my chest, scalding me. And I thought, oh my gosh, open system now. And it was definitely exchanging with its surroundings because there I was spilling hot soup all over my chest, burning my chest in the meantime. Let me tell you, I got some bad burns off of it too. And this woman's like sitting across and she's giving me the disappointing look like, you shouldn't have been eating, but I was just drinking something hot. Of course, I gave her a nasty look back, but it reminded me of thermodynamics, like that isolated system. That thermos was not affected, so it never cooled down. So there was like boiling soup, so once it became open, it definitely exchanged with the surroundings, me namely. Okay, so funny story, but it might get you to remember those two terms. System, okay, that is under study can be either open or isolated. Okay, so what is not the system? Well, that's all the surroundings then. So that's like just write everything else. Everything else. So once that soup canister became open, I was the surroundings. The soup was still like the open system, or that thermos was the open system now, and I was the surroundings being affected by it. Okay. So, we need to pinpoint these things because sometimes we'll look at the surroundings to see how they can affect the system, or we'll just be looking at the system and how it can respond. And usually that system that we're talking about is usually going to be a living thing, okay? Like that worm or something. All right. So we're still in, this laws and transformations. So we just got a few terms under our belt here. So now we're actually going to talk about the first and second laws of thermodynamics. Okay, sounds so impressive again. The first law of thermodynamics, and you know these, the law of conservation of energy. You've heard of conservation of matter. Well, there's also conservation of energy. And it's the same kind of thing. Energy can be transferred and transformed, but it cannot be created nor destroyed. Now, that is only if you're talking about a closed system. So let's write this out first. Energy is transferred, going from one place to the other, or transformed, changed in form, right? But energy is transformed or transformed, but cannot be created nor destroyed. But cannot be created nor destroyed. Now, when we talk about this, we talk about in the universe. So we actually consider our universe, excuse me, almost like a closed system then. Okay, so this is only in isolated. Sorry, I say closed sometimes, the same thing. Open, closed, isolated systems. Okay, but we consider sometimes, like science greatly considers the universe almost like there must be an end to it. So it must be closed in some sort of way. We haven't found that. And even with living things, we haven't found an end to life, so all life is an open system. So even though we want to obey the laws of conservation of energy, as living things, we take in energy, but we always release energy. And so we are an open system, okay? And we're going to affect the surroundings, okay? So that's the law of conservation of energy. And again, you could think of some examples like an electric company converts nuclear or sunlight or wind into electrical energy. That's kind of the way law of conservation can be transformed, but they can't create it or destroy it. They just have to transform it. So they have to get it from another source, transform it to another. All right. Then there's the next one. I call this second law the law of disorder, entropy. Okay. I don't know what it's actually called, like to be exact, but it has to do with this idea of what is entropy. Entropy is disorder. Okay. And every energy transfer or transformation is going to increase entropy or disorder in the universe. So let's write that down. So every transfer or transformation of energy will hold on. Lost my train of thought here. Will increase entropy. Okay, so we're getting more disordered. And sometimes if you think of like your house or your bedroom or something like that, like every time something's going on in your life and you got a lot of energy that you're putting into like a test or you're doing this right now, there's going to be disorder happening around you, because if that energy gets channeled into one thing, it comes from something else. So something else gets sacrificed. And I always think of that around my house. Okay. And again, we'll be looking at Gibbs free energy equation, which will like take into consideration energy, heat, temperature, and entropy. So know that word, entropy. Okay. All right. So that's the second law, the disorder one, I call it. All right. So next thing. So number one was the terms. Number two was the first and second laws. Number three is, what is free energy? Now you see how I wrote this word available next to it, and then I have this word spontaneity. Isn't that a great word, spontaneity? What is free energy? It's spontaneity. Free energy is actually, I want you to consider it available energy. We will call this thing Gibbs free energy equation that we're going to be learning, but I want you to think of free energy as spontaneity. And there's a few things I want to say, two very important things I want to say about free energy and spontaneity. Number one, entropy of an organism. Okay, just listen to me first. The entropy of an organism may decrease as long as the total entropy of the universe increases. What does that mean? That means an organism can become more orderly, and that's what life is. You know how like we have cells that make up tissues, that make up organs. We're very orderly, and an organism can become, less entropy or more order. Okay, its entropy can decrease as long as the universe increases. So let me write that down now. So entropy of an organism, okay, may decrease. So remember how we just said this law, like entropy is always going to increase and everything? That's the law of thermodynamics. You should always get more disorder. Now we're saying entropy, the disorder of an organism, may decrease. So we may become more ordered as long as total entropy of the universe increases. Total entropy of the universe increases. Okay, so what is this saying? This is saying entropy of an organism may decrease. So in other words, we can become more orderly as long as total entropy of the universe increases. And then it obeys that law, because there will be people out there that want to question biology and especially evolution, because evolution actually leads to more order, okay, according to the needs of the environment. So like, how can we become more ordered when and people that are against evolution would always say, oh, it doesn't follow the second law of thermodynamics, but it does, because an organism can do this. So there's this saying out there that we are islands of low entropy. Organisms are islands of low entropy. That's what an organism is. An organism living in a world that has high entropy. So we are islands of low entropy in an ever random universe. In ever more random universe. And that obeys the second law of thermodynamics. And that's it for that right now. Okay?